Okay, working on 13.3, which is, what is 13.3? Fundamental theorem of line integrals. So for number 3, it says determine whether or not f is a conservative vector field, and if it is, find the little f such that our vector field is equal to the gradient of the scalar function f. So first of all, is this conservative? Well, there's a quick check. If this is a two-dimensional vector field, which it is, then I just need to check the partial of q with respect to x. Does that equal the partial of p with respect to y? Now, I think I'm probably in my notes I had that written the other way. Yeah, I did. Doesn't matter. Okay, but I'm going to stick with what I have in the notes. So partial p, I want to check this. Partial of p with respect to y equal to partial of q with respect to x. Now this is our p, this is our q, all right? So what is the partial of p with respect to y? It is -3. And the question is, does that equal the partial of q with respect to x? And look, we get -3, so check. It is a conservative vector field. Since it's conservative, it must be the gradient of some scalar function, and we need to determine what that scalar function is. So now that we know that it is, we know that this piece right here must be the partial of the scalar f function with respect to x. This must be the partial of the scalar f function with respect to y. And that's because that's what this is, right? Gradient, partial with respect to x, partial with respect to y of the scalar function. So now to work through this, we're going to use partial integration, right? So I'm going to first write down this first piece. I know that the partial of the scalar function f with respect to x is 2x minus 3y. Now what I'm going to do is I'm going to integrate this. So I know that the scalar function f must be the integral of this with respect to x, which is the integral of 2x minus 3y with respect to x. And the antiderivative of 2x with respect to x is x squared. Antiderivative of -3y with respect to x is -3xy. So remember, antiderivative of this, we treat all of it like a constant, right? Integrate that with respect to x, so an x appears. But then we have this constant of integration. And the thing about this constant of integration is that whatever's over here, if I were to take the derivative of this with respect to x, right, I should get this back. So it could be possible here that I have some function of y over here where all I have are y's and constants. In that case, if I took the derivative of this with respect to x, this would be 0. So I'm assuming that this is something that has y's and possibly constants or just constants in it. I know that the derivative of it would be 0 if I tried to take the partial with respect to x. So I don't know if it has y's or not, but I have to act like it might. So that's what I know f is so far. Remember, we're trying to find f, right? That's what we're trying to find. All right, well, now what we do is we use this information. We know that the partial of f with respect to y has to be equal to this. So I know that the partial of f with respect to y must equal -3x plus 4y minus 8. But that implies that if I take the derivative of this with respect to y, which I'm about to do, what is the derivative of this with respect to y? We get -3x. And then the derivative of, well, x squared, that was 0. Derivative of this with respect to y, I'm going to say is the derivative of g with respect to y, which I could have just written g prime, but I'm going to do that instead. I know that this derivative, right, must equal this piece, -3x plus 4y minus 8. And you can see here I can cancel, this is an equation, I can cancel this out. And what I get is that the derivative of g with respect to y is 4y minus 8. Now remember, I wanted to know what f was. Here's what f is. I just needed to figure out what this function of y was. Well, I know that the derivative of it is this, so that implies that g itself, right, should be equal to the antiderivative of this with respect to y, which is 2y squared minus 8y. And remember we said that g, sorry, I should write g of y, that's fine. G of y is this, that could possibly have y's, right? We said it could have y's in it. Well, it looks like we do. And possibly a constant, which I'm going to put plus c here. So now I think I have f, right? I knew that f was this plus some function of y, and I'm pretty sure I know what that function of y is. So let's write down our conclusion. Our conclusion is that f, and you could write it f of xy if you want, is going to be x squared minus 3xy plus this 2y squared minus 8y plus a constant. And the good news about this, or the good news is that we can check our answer. So I'm claiming that this is the scalar function that when you take its gradient, you get that vector field. So let's try it. What's the partial of this with respect to x? So 2x here minus 3y with respect to x, 0, 0, derivative constant 0. So that's the partial with respect to x. Partial with respect to y, 0, negative 3x, plus 4y, minus 8, derivative constant 0. So let's see, do they match? This is this, and this is this. So that's it. That was right. That was the potential function. All right. Let's try one that might be a little bit more difficult. Maybe 7. 7 looks like it might be messy. So for 7, we have our vector field. It's two-dimensional. Y e to the x plus sine y, and then x squared minus 2x y to the negative 3, and that's it. All right, so let's see. First of all, is this a conservative vector field? Let me see if this student wants to come in here for a minute. Do you want to come in for a minute? Sure. Yeah, come on. I'm going to finish up this problem, then we can talk. All right, so this is P, this is Q, and I'm going to check to see if it's conservative first. So is the partial of P with respect to y equal to the partial of Q with respect to x? Well, partial of P with respect to y, so this is a constant, derivative of y is 1, so we get e to the x, and then derivative of this with respect to y would be plus cosine y. All right, is that equal to the partial of Q with respect to x, which would be 2x, hold on a second, P with respect, so 2x, and then this doesn't look like they're the same. So, did I write it down wrong? Let me make sure I wrote it down right. Y e to the x, so, oh, I wrote it down wrong. I was going to say, that didn't look right. That didn't look like it was going to work out. What did I do? I wrote down, oh, number 8. Sorry. This is e to the x plus x cosine y. There we go. That'll work. Okay. Partial with respect to x is derivative e to the x is itself. And then derivative of x times a constant. This is going to be plus cosine y. So check. This is a conservative vector field, so we need to try and find the scalar function such that this is the gradient of that scalar function. So I'm assuming I know that this is the partial of the scalar f function with respect to x, and that one is the partial with respect to y. So I'm going to start off the same way. I'm going to set up, I know that this is equal to y e to the x plus sine y. And if I want to know what f is, then I'm going to integrate that with respect to x, which means I'm going to integrate this with respect to x. And y is constant here, so remember, I'll cover that up. Antiderivative of e to the x is itself, so I get y e to the x, and the antiderivative of this would be x sine y, plus possibly a constant, but again, that constant can have y's in it, so I'm going to call that g of y. And that's what I know f is so far. Now, I'm going to take the fact that when I take the partial of this with respect to y, I should get this. So I know that e to the x plus x cosine y must equal this with respect to y. So we get e to the x. Then here, derivative of sine y is cosine y, or sorry, cosine y, but then there's an x in front of it, so x cosine y. And then plus the derivative of g with respect to y. And check this out, these cancel out both sides. Boom, 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 boom. So that means 0 equals the derivative of g with respect to y. And the only way that that's going to happen is if g itself was a constant, right? If g of y was a constant. So now I come back here, this is what I knew f was, and I just tack on here g of y, which we said was a constant. And this should be our potential function right there. So that is number 7. Now, there aren't any three-dimensional ones here, not till later. Okay, I'm gonna do one more. Ramiro, is that okay with you? You got a quick question or something? No? You sure? All right, so I'm going to look at number 15. So number 15, this will be the last one I do. We're given a vector field. This time it's three-dimensional. It is, okay, yz e to the xz, then e to the xz, and then xy e to the xz. So we're given a vector field. We're given a curve, C, and it's given by the parametric curve written in this vector form. It's t squared plus 1. It's t squared minus 1. And finally, t squared minus 2t. And t is going to vary from 0 to 2. Okay, so you can do this problem, and you can make this a disaster, like a really, really difficult problem. Or you can use the fundamental theorem of line integrals, which says that if the vector field is conservative, in other words, if it equals the gradient of some scalar function, then the line integral over C, right, of f dot dr should be equal to the line integral over C of the gradient of f dot dr, but that should be equal to f, the scalar function f, evaluated at the two endpoints of the curve. So this minus f of r of a. Shit, I'm out of room. This is equal to f of r of b minus f of r of a. But that's only if this vector field is the gradient of this scalar f, which means that we would have to find its potential function. Your only other option is to actually plug in, for x, plug in all these, plug in y's in here, and then you would have to take the derivative of this and you'd have to dot it, and you do it the traditional way, and that, good luck, have fun. I'm going to go for this instead. I'm going to hope that this is true. Now, at this point in the class, we don't have a way of checking to see if this is a conservative vector field because it's three-dimensional. If it were two-dimensional, we'd be able to do it with the partials, but it's three, so we can't. Later on, we'll have something. So I'm just going to guess that maybe it is, okay? So I think this is the gradient of something. If it is, that's the partial with respect to x, that's partial with respect to y, and that's partial with respect to z of that scalar function. So doing what we did last time, I'm going to assume that this is equal to yz e to the xz. Now, if that's true, then f must be the integral of this with respect to x, which would be treating y and z like constants. And so the antiderivative of e to the x is itself, but then that z there, we got to scale by it. So in other words, if you're trying to integrate like 4x, the antiderivative of this is 1/4 e to the 4x. So that 4 up here is like the z, or the z is like the 4, so we have to scale out by it. So that's actually a good thing because it's going to come out here and kill that z off. So we get y e to the xz. And double check it, that's a constant derivative of that. The z would pop out, we should get this. Plus a constant, but that constant could have y's in it, right? This thing out here could have y's or z's, because when I take the derivative with respect to x, if I see a y or a z by themselves, the derivative is 0. So I'm going to say that this out here is some function of possibly some y's and some z's, and maybe there's some numbers in there, but it does not have x's in it. So that's it so far. Here's what I know f must be. Now, I know that this right here, right, this partial, so I know that e to the xz, that must be equal to what I get when I take the derivative of this with respect to y. So let's do that. Derivative of this with respect to y. Here's y. This is all a constant. So derivative of y is 1. So you get e to the xz plus, now the derivative of this with respect to y, which is g partial with respect to y. And that's a really good thing because these cancel on both sides, you can see. And that means that g, the derivative of g with respect to y must be 0. So what does that tell me? If I'm saying that the derivative of g with respect to y must be 0, then that means that g of xy, of yz, does not have any y's in it, right? Because the derivative of it has to be 0. So the only thing I could have in there that in terms of y's are just constants. But I could have z's in there. Because if I take derivative of g with respect to y and I have some z's, those are all going to go to 0. So what I know right now is that this g function does not have any y's, but could have z's. So I'm going to call it, I don't know, it's some function of just z. All right, so now, let me summarize where I am. F is equal to this right here, y e to the xz. But this g of yz, I already said, has to be just have z's in it. So it's just some function h of z. And now I go to my last piece of information, which is this. I know that xy e to the xz must be equal to the derivative of this with respect to z. And the derivative of that with respect to z would be, let's see, y is there, derivative of this, the x would pop out, so you get x, y, e to the xz, plus the derivative of h with respect to z. And again, these go away. This is too easy. 0, h, z, and that means that your h function had to be a constant. I'll use c. Now you can say for sure it's a constant, and it doesn't have any z's in it because derivative was 0, but it could have a constant. So I know that this is some constant. So my final result is that my scalar function f should be equal to y e to the xz plus a constant. And this is my potential function. So if I take the derivative of this with respect to x, I should get this. With respect to y, I should get this. With respect to z, I should get this. You can check it yourself. Now, all the hard work's done. The only thing I need to do now is, see what we're doing is we have this curve, three-dimensional space, C, and instead of trying to integrate over the whole curve, we're using the fundamental theorem of line integrals that says all we need to know is what is the value, what are these points, what are these endpoints, and then plug those endpoints into the scalar function, and that gives us the work done. So let's see, t was 0 to 2? T was 0 to 2. So what I need to do is figure out what's r of 2, and then what's r of 0. So r of 2, we just plug 2 in here. We get the vector 5, 3, 4, 0. Okay, and then if we plug in 0, we get 1, -1, 0. And now I'll just do the fundamental theorem of line integrals now. So we were trying to look for the work, which was f dotted with dr, but that turns out to be the gradient of f, scalar f, dot dr, but that turns out to be f evaluated at the two endpoints, right, subtracted. So what are the two endpoints? If we write these as points, this is 5, 3, 0. And if we write the other one, 1, -1, 0. And I'm plugging those values x, y, z into this. So we get, let's see, 5, z is 0, so 5 times 0 is 0. E to the 0 is 1, and then y is 3, so we should just get 3 here. Minus, now, see, z again is 0, so that's going to be just 1 here, and then the y is -1, so we just get -1, and so we get 4. The work done is 4. What's that number? Which one was this? 15? Yeah, it's 4. So we're done. Just as an appreciation of how much work that saved us, is if I had stuck with the original, which would have required us to turn this into this and not use fundamental theorem of line integrals, we would have been integrating from 0 to 2. The vector, it's the f vector, but evaluated on the curve. So I would have done, let's see, y, which would have been t squared minus 1, times z, which is t squared minus 2t, and then e to the x t squared plus 1, times z, which is t squared minus 2t. Okay, that's the first part. Then e, right, e to the x times z, so t squared plus 1 times t squared minus 2t. Then this one right here, shit, that's going to suck. T squared plus 1, and then y, t squared minus 1. I'm going to run out of room. E to the xz, which would be e to the t squared plus 1, t squared minus 2t. I'm probably off the camera. It's okay. I'm going to take that vector. I'm going to dot that vector with the derivative of this, which would be 2t, 2t, 2t minus 2 dt. And then when you dot, imagine taking 2t times that plus 2t times that, plus this times that, putting them all together and integrating. That would be a disaster. So by getting the potential function, we're able to get around all of that work. We just had to be able to show that it was a conservative vector field. So that's it.